Okay, yeah. All right. So the last talk of the workshop. It's a great pleasure to have Anand from MIT, who will give a succinct talk on some arguments for QMA. And the classical analog uses PCP. The quantum analog will not use quantum PCP, but it could have.
Okay, great. Thanks for the intro. Yes, I will indeed try to make this succinct. Thanks everyone for sticking around till the end, till the bitter end. So, okay, so just first a review of some basic terminology. So I think we all know what an interactive proof is. So basically when we talk about a proof system, we mean that there's some interaction between a prover and a verifier. If the answer to our problem is yes, then the prover should be able to convince the verifier that the answer is yes. And if the answer is no, then no kind of false or cheating prover can convince the verifier to falsely accept. And this property is called soundness. And when we talk about a proof, we typically mean soundness against all potentially computationally unbounded provers. Like there's no computational restriction on their power. An argument system is basically the same thing, except you weaken the soundness condition. You say that you want soundness only against computationally bounded provers. And I guess typically, like the way this is actually formulated is you say you want soundness as long as the prover cannot break the hardness of some cryptographic assumption. So that's what we'll mean by argument. In this talk, I'll talk about proof systems that are in kind of weird models, like multi-prover models. But when I say an argument system, I'll always mean a single prover argument. So there's a single prover interacting with the verifier. And moreover, all of my arguments will have the property that the honest prover correctly executing the honest strategy will not require some ridiculous amount of computational power. So even though there'll be arguments for powerful classes like QMA, the actual power required by the prover will be just polynomial time on top of maybe having a witness for the QMA problem. So the idea is if someone hands you the solution, then you could prove the solution is correct in a reasonable amount of time. Okay. So what is a succinct argument? I guess in general, you want the spirit or the name of the game here is you want the communication between the prover and the verifier to be as small as possible. So ideally, much smaller than the size of the witness for the problem you're trying to check. And for us, what I'm going to define as like the gold standard for succinctness is if I have a problem instance of size n, then I want the communication between the prover and the verifier to scale polylogarithmically in n. And I also want the verifier's runtime to be polylog in n plus a term that's linear in n, sort of that's necessary just for the verifier to read the input, right? To read the instance that it's checking. And also these runtimes all conceal like a scaling in the security parameter of the crypto system, which will in general be polynomial. So we can scale polynomially in lambda. I guess this is sort of okay because typically the security of your crypto system will scale some negligible function in lambda, so lambda doesn't need to be very big. Like lambda won't need to be polynomial in n or something for you to get a reasonable security.
So,
yeah.
So is lambda about soundness?
Yes. Yeah. Lambda will show up in the soundness.
And why do you need a lambda? Why don't you just set it to be 1 over n?
Oh, I mean, it's you need in general, you need a lambda to control like the chance you'll have an error from like the maybe the prover can like break your security assumption. Like you can, I guess, typically set it to be, so lambda is bigger than 1, and you can typically set it to be, I guess, like order logarithmic in n, or yeah, maybe smaller. I'm not sure. Okay, so what's the story of these things for NP? So first of all, if we talk about interactive proofs for NP, like observe that just the definition of NP says that there's a non-interactive proof for NP. It's just I give you the witness and you check it. So that's very straightforward. What about succinct arguments for NP? So here, sort of the only thing that's interesting is like can we achieve succinctness? Like in the non-succinct case, like we've already achieved proofs, which is like the gold standard. So Killian in 1991 famously showed that there is a succinct argument system for NP using the PCP theorem plus a type of succinct commitment. So at a cartoon level, what does his protocol do? It asks the prover, it's just trying to prove to you that it solves some NP problem. It wants the prover to find a PCP proof of this statement. And then it says commit to this PCP proof in a succinct way using a construction called a Merkle tree. So what does this look like? The prover has this big PCP proof, which consists of many symbols, and it's going to compute a commitment in this tree-like fashion. So it's going to take symbols. It's going to take maybe 2 symbols at a time and like apply some hash function and get a value, and then take this layer of hash values and then like hash it together again, and so on and so forth until you get a root value at the top. And this root value is all that you report as the commitment to your PCP proof. Okay, so you get this commitment, and now it's going to say, okay, you committed to this thing. I want to check that your thing is actually correct. So I'm going to ask you to open the commitment at a few locations. And the nice thing about this tree structure is that I can open one position in the string I'm committing to while only sending an amount of data that scales with the length of a path from the root to the leaf here. So I just have to tell you, along this path, for each hash value, I have to tell you the 2 things that feed into the hash function and say that they actually, hash to the value that I claimed. So that's much less. That's a polylogarithmic amount of communication compared to the number of leaves you have down here. So you do this. You check that the prover can open, at randomly chosen positions, and then you check that the values you observe in those positions also are accepted by a PCP verifier for your NP language. So that's how that works. Okay. So this is great, and this requires very minimal cryptography. Like it just requires, I guess, like these hash functions to construct commitments. And the prover is polytime, except it needs like this PCP proof, and that's that's not efficient to find, but we can assume it has it. Okay, now let's move on to quantum classes. So the quantum analog of NP is QMA. So what's the story with QMA? Well, first you might just ask, like, what is the interactive proof story for QMA? So there's sort of a trivial thing you can say, which is that QMA is contained in p-space, so therefore it has an interactive proof. But this interactive proof is kind of useless, right? Because if you look at what the prover is supposed to do to prove the answer to a QMA statement, like it has to basically reduce QMA to a p-space problem, and then has to compute all these like giant sums over finite fields, and yeah, you're not going to actually do that with an efficient device. So this doesn't satisfy the efficient prover criterion. However, so this is in the world of one prover exchanging classical messages with the verifier. In the world of 2 provers, it was shown by Reichardt, Unger, and Vazirani, and sort of simplified by Grillo, and there's been a lot of work in this area, that there is an interactive proof for QMA with efficient provers in this 2-prover entangled model. This is this model called MIP star. So in this model, you have a classical polynomial time verifier. You have 2 entangled non-communicating provers. So the provers are quantum. They get to share an entangled state, but they're not allowed to communicate during the interaction. And the provers are efficient in that they run in quantum polynomial time, and they're just given copies of the witness state for your QMA problem.
Whenever you say provers are efficient, you mean the honest provers?
The honest provers are efficient. That's right. So the soundness still holds against like any cheating prover of any efficiency. Cool. Okay. So that's the state of like interactive proofs for QMA. What about arguments? So actually, I'll remark here, like already, it's kind of interesting. There's no like non-interactive. Well, sort of by the nature of things, like unless you believe QMA is contained in NP, there's not going to be like a non-interactive proof for QMA. And also, like in the classical case, sort of the only interesting question was like in passing to the world of arguments, can you make things succinct? But here there's also sort of the classical versus quantum and single versus multi-prover dimensions at play here. So like it's already interesting to ask, like, can I have a classical interactive argument for QMA with one prover? Like that's not at all a trivial question. Okay, so in fact, we now know sort of 2 approaches to this question. The first approach dates back to Mahadev's work from 2018. So this, I guess, was, I believe, sort of like in the paper, maybe it's stated in terms of BQP, but all the ideas sort of port over to QMA as well. The approach was this. So in this paper, Mahadev constructed a protocol that I guess people call the measurement protocol. And you can think of it as a sort of weak commitment to a qubit. So it's a way for a prover to send a classical message and say, I've committed to holding this qubit, and now I can open this qubit for you in either the Pauli X basis or the Pauli Z basis. And then using this, you can kind of check any language in QMA by saying, prover, please find the QMA witness state. So first reduce your QMA language to checking the energy of a Hamiltonian whose terms are expressed in the Pauli X and Z bases. This is a standard thing you can do. Then ask the prover to prepare copies of this ground state and commit to them using this weak commitment, and then open them in the appropriate bases and check that the energy is correct. So this is her protocol, and this gives you a classical interactive argument for QMA. So that's approach number one. Approach number two came a bit afterwards, which is to start from the two-prover interactive proofs and then transform them into arguments by some more generic procedure. So this is, in particular, there was a paper by Kalai, Lombardi, Vaikuntanathan, and Zhang in 2022 that proposed a general compiler that can take any MIP star interactive proof protocol and it will spit out a single prover interactive argument. Now, they didn't prove that the resulting argument system is always secure. Like they just proved sort of that classically this transformation works, but it's not known sort of whether it works in general in the quantum case. So, but it at least gives you a way to construct a protocol, and then for your specific protocol, you can try to analyze it via more or less ad hoc ways. So this, past work with Tina Zhang and myself, we showed that if you take this and you apply it to one of the interactive proofs for QMA on the previous slide, specifically the one due to Grillo, you get an interactive argument for QMA. So, okay, so we have interactive arguments for QMA through two different techniques. Great. So now, what about succinctness? Like, how are we going to make these things succinct? So you might try to start with the Mahadev-based approach and try to make it succinct. So this has indeed been tried. So there's a paper, and I guess we've all observed that cryptography papers are very long. Sometimes even the lists of authors are very long. So this paper by Bartusek, Kalai, Lombardi, Malavolta, Vaikuntanathan, Vidic, and Zhang in 2022. So they gave a succinct argument system based on the Mahadev measurement protocol. Unfortunately, it had to make a non-standard cryptographic assumption, which is post-quantum secure indistinguishability obfuscation. So this is not yet known from standard cryptographic assumptions. So what did they do? They kind of took this Mahadev protocol and they applied many nice tricks to it, but sort of the biggest trick was like they kind of combined it with a Killian-style commitment, or the specific object they used was something called a post-quantum succinct argument of knowledge. And they used ones that were constructed in these works by Chiesa, Ma, Spooner, Zandri, and Lombardi, Ma, Spooner. Hopefully I'm getting the names right here. So these are sort of essentially like the Killian protocol, and there's some quite delicate analysis in here that shows that this thing is still secure in a quantum world, but the protocol itself is not too different from the tree thing I showed you. Now, the snag here, why do they need this kind of strong cryptographic assumption, is that the Mahadev commitment actually requires a fresh key for each qubit you commit to, because there's some problems otherwise with like leakage in between the different qubits. And so they used I/O to compress like a procedure that would generate fresh keys for each qubit. So this is, to my knowledge, the only place that I/O is used in this work. Okay, so that's what we know about making that approach succinct. Now, what if we tried to make these compiled MIP stars succinct? So this here, it seems like the idea again is quite simple. It's like we said there was a general procedure for taking any MIP star and turning it into an interactive argument. So just find a succinct MIP star for QMA and apply the compiler to it, and you're done, right? What could be easier? So okay, there's two problems with this. The first is what I already alluded to. There's no general soundness theorem for this compiler. So this is, to qualify this a little bit, there was a recent work in 2024 that showed that there is a sort of general security statement, but it's a little bit too weak to use for cryptographic purposes. Like it says something like, in the limit of the security parameter going to infinity, the success probability of the provers will converge to the two-player value, but they don't control how quickly this happens in the security parameter, so you don't actually know that it's like decaying negligibly. So you don't know how big the security parameter has to be to achieve some target value of security. So you need to kind of analyze the resulting argument system from scratch. Okay, so that's problem number one. And then problem number 2, which actually gets into why this talk is showing up in, well, maybe this is why I was invited to the reunion workshop in the first place, is so there's no known succinct MIP star proof system for QMA with efficient provers. This thing, it is known. So the MIP star model is, it turns out, actually quite ridiculously powerful. So it's equal to RE. You can decide undecidable languages with an MIP star proof system. And this does imply that there's an inefficient proof system for QMA with very short messages indeed, something like constant size questions and polylog sized answers. But the provers are really like ridiculously inefficient in this thing. So it's no use for our purposes. Sorry?
They're better than P-space?
I think they might be worse than P-space. I think they're like NX or something. Yeah, yeah. So yeah, so it's worse than just doing IP equals P-space. And then in 2018, Tomavidic and I claimed a construction of such an MIP star, but our proof contains an error. And I spoke about the error in this proof during the spring semester. So if you want to know more about that, you can go look at my talk. And we also wrote a little document on this, Chinmay, Nirke, and myself. So that's that. OK, so there's no known succinct MIP star proof for QMA. Some people call this the quantum games PCP question, by the way. So yeah, so we don't have such an object. So it seems like we're maybe doomed for like constructing a succinct MIP star or a succinct interactive argument through this route. So the message of this work is essentially that you can get around these obstacles. There is a way to construct a succinct interactive argument for QMA via compiling an MIP star and doing so in a kind of sufficiently clever way. And really the thing that we exploit is that succinctness, there's really 2 parts to it. There's 2 important things you have to do to achieve succinctness. So there's the question of there's question succinctness, which is like that the challenges sent by the verifier to the prover should be short. And then there's answer succinctness, that the messages sent back from the prover to the verifier should be short. And these kind of can be achieved by combining different techniques. So if we actually look at the 2 approaches we saw, they kind of each like founder in a separate part of this. So question succinctness, in the MIP star world, there's actually lots of very nice tools for achieving this. Like this turned out to actually, this is sort of in some ways the heart of the MIP star equals RE proof is the ability to get very short questions for things that you can't do with such short questions classically. And now some of the tools have been simplified a lot. So there's this great paper by Michael de la Salle that has a nice clean statement of one of the key techniques for achieving this. So this type of succinctness is easy to achieve in the MIP star world. However, in the Mahadev style world, like this thing is difficult. Like this is where you run into the fact that every qubit needs a fresh key, and you need to send all these keys, and you need to use I/O to compress the keys. So this step is hard. On the other hand, answer succinctness, which is getting the responses from the verifier to the prover to be short, this is actually kind of hard in the MIP star world. So the only way we know of doing this is to take a classical PCP proof that the prover's answers are, oh, I think I swapped prover and verifier in this slide. Sorry about that. But the words challenge and response are correct. So hopefully that helps you interpret this. So in the MIP star world, the only way we know of doing this is using a classical PCP to prove that the answers you would have sent were actually correct, which kind of requires reducing whatever problem you're studying to a classical problem. So like if you're trying to do this for QMA, it will force you to like reduce your QMA problem to like an NX problem or something, and then compute an exponentially large PCP for that or something like that. And so this is the step that requires the inefficient prover. However, in the Mahadev style approach, like this is actually quite easy. Like this can be done almost in a kind of black box way by using these post-quantum succinct arguments of knowledge. So so it'd be nice if we could kind of combine the strengths of both of these approaches. So this is exactly what we do. So here's the approach that we take in this work to constructing a succinct argument for QMA. So the first thing we're going to do is we're going to start in the MIP star world. We're going to construct a question succinct MIP star for QMA with efficient provers. Okay, so this thing will have long answers from the prover back to the verifier, but the challenges sent from the verifier to the prover will be short. So what do? We take the Grillo protocol, which naively doesn't have any sort of succinctness, and we kind of, I guess, upgrade the components a bit. So one of the key components in this protocol is like a test for that the two provers share an EPR state and that they measure it in the appropriate Pauli basis. So that test can be kind of just sort of, you can drop in as a replacement for it, this improved result of de La Salle. So that's great. And then there's also a part of this that kind of depends on the QMA instance you're actually checking, like the local Hamiltonian you're checking, and this thing might have many terms in it, and you might have a lot of to communicate for that. But this can be kind of improved using a little PRG magic. So this is actually a trick we stole from the BKLMMVVY paper. And okay, I will say this part uses PRGs, but it is actually sort of assuming you have assuming that PRGs exist, like the resulting object you get is still actually a proof system, like it's still sound against unbounded provers, which is a little weird, but as far as I can tell, true. So next, you take this resulting MIP star and you compile it to a question succinct interactive argument. So here the protocol itself is just like literally you take this KLVY compiler and you slap it onto your MIP star, and what you get is what you get. Analyzing it is not you have to do some work. This is actually where most of the work in our paper goes, is analyzing this object. And it really requires analyzing the KLVY compilation of de La Salle's EPR test. So this is where most of our sweat went into. And this step also requires sort of some cryptography, actually the strongest cryptographic assumptions in this work. So this step requires quantum homomorphic encryption. It turns out to not really require like fully homomorphic encryption. Like I guess it's like leveled homomorphic encryption or something, sort of because the circuits you're required to homomorphically encrypt are extremely simple circuits. But this thing still, like the only constructions we know are from like LWE or maybe slightly weaker assumptions, so fairly high up in the crypto hierarchy. And then finally, we take this resulting interactive argument, and now we can make this thing answer succinct. We can compress the answers in it by using this post-quantum Killian style thing. So this is almost like a black box kind of thing. And this also requires only collapsing hash functions. So this is a relatively modest cryptographic requirement. So with these steps, this is basically how we get our protocol. Okay, great. So now I can sort of flash the theorem at you. So what is the theorem? Well, assuming that all the things I said you need to assume exist, then there's a constant round classical verifier argument system with a constant soundness gap for any promised QMA problem where you have sort of the following parameters. So like the honest prover is quantum polynomial time as long as it gets copies of the QMA witness state. The honest the verifier runs in time that's like polylog in, I guess, polylog n, but really we wrote it as polylog in terms of the QMA verifier circuit size. This thing t is itself a polynomial in n, so it's still a polylog n, polynomial in lambda, the security parameter, and this O tilde of n, which is the time it takes to read the input. And the amount of communication is polylog n times polylambda. So that's succinct as I defined it at the beginning. Okay, so any questions about the result or the overall like structure of how we got here?
How many copies do you need?
Oh, I think we need a polynomial number of copies because you have to kind of amplify the energy gap. Like you have to sort of do like a big joint measurement of many copies to get this constant soundness gap. So yeah.
By the way, I think that the first assumption might imply all the other ones.
Oh, the quantum homomorphic encryption
I
implies.
think that implies like collapsing hash functions, which is all you need
Oh.
for the second thing, and then also implies one-way functions.
Oh, cool.
The third thing.
Okay, great. Okay, so I can cover this up.
Yeah.
Okay.
Yeah.
Thanks.
How does FHE apply collapsing hash function?
It's through this like somewhere statistically binding hash function thing. Yeah. I can.
That's very nice. Thanks. Okay, so in the rest of the talk, I'm going to tell you a little bit about how the analysis works. Not everything, but just like a tiny bit. and then say a little bit about maybe connections to quantum PCP at the end. Okay, so the starting point, I want to start by just showing you so I'm not going to talk at all about the final step, like the part where you get answer succinctness, because that part is really black box and we have no new contributions there. I'm only going to talk about the first parts, which are the construction of the question succinct MIP star and how you compile it. So I'll start out by just showing you the Grillo MIP star for QMA. So I guess I should have written on the slide as well. This is going to be the Grillo 2017 protocol. So how does this protocol work? Well, it's an MIP star, so there's two provers. They share some entangled state. So in this case, the honest entangled state is some number of EPR pairs, some polynomial number of EPR pairs. And in addition, Alice is going to hold just in her private register a copy of the QMA witness, or maybe some multiple of copies. And OK, so there's now a classical verifier. And now the verifier is going to interact with these two provers, and it's going to do one of two things with them. So part of the time, it's going to engage in some protocol called the Pauli basis test. I'm not going to tell you anything about the internal structure of that protocol, but that protocol will essentially ask the provers to measure their qubits in the Pauli X or Z bases and maybe some additional test questions that reveal some information about what they're doing. And then some other fraction of the time, what will the verifier do? It will send Alice the question teleport. So it will say, I'm going to instruct you to use your EPR pairs to teleport your copy of psi over to Bob. OK, and then Alice will dutifully do this and report back the teleportation corrections to the verifier. And what will Bob get? Bob will get a question that looks exactly like one of these Pauli basis questions. He'll be asked, measure your qubits in some combination of Pauli X and Z bases, and report them back to the verifier. So why is this a good thing to do? So let's write down what a QMA problem looks like. So here's like a kind of QMA complete problem. I give you a local Hamiltonian, which is a sum of a bunch of terms. And let's say each term is, it could even be like a tensor product of Pauli operators, right? And I want to ask, is the energy of this, is there a state where the energy of this Hamiltonian is below some threshold A, or is it above some threshold B for all states, right? That's the local Hamiltonian problem. So I'm going to claim that this can help me decide the local Hamiltonian problem. How's it going to do that? Well, first, the Pauli basis test, the guarantee it will get me is that when I tell Alice and Bob to measure their share of their shared qubits in either the X or Z basis, they will do as instructed. That's the theorem you can prove about this test. And now, once you can do that, you can combine their measurement outcomes to obtain a measurement of the energy on psi, the QMA witness. What do? You ask, when you ask Alice to do this teleportation, she gives you the teleportation corrections. You ask Bob to measure some Pauli operators corresponding to the Hamiltonian term you care about. And then you just apply the Pauli corrections to the measurement outcome he gives you, right? So the Pauli corrections will be some product of X and Z operators, and you can kind of compute easily how they should modify the measurement outcomes you get to tell you the measurement outcomes of the operator you wanted to measure on the state. So that's sort of at a high level how this protocol of Grillo works. Any questions on this? Cool. OK, so this thing is not succinct. It's not question succinct for a couple of reasons. One reason is that the Pauli basis test, whose details I've not specified, is itself not question succinct. It involves sending information about every qubit you want to measure. And also, this Hamiltonian test turns out to not be succinct if you want to get a constant completeness soundness gap, because you're going to have to actually ask for the Hamiltonian to be measured on many copies of psi, and you have to specify a different randomly chosen term on each copy of psi. So how do we get a question succinct MIP star for QMA? Well, we kind of want to de-randomize both parts of this. So to de-randomize the Pauli basis test, this is kind of directly what de La Salle does. If you happen to know the BLR tests for linear functions from the PCP literature, there's also a classic result, which is like a de-randomization of the BLR test using epsilon bias sets. And this you can really think of as almost the equivalent statement, but for the Pauli group rather than linear functions. So it also uses epsilon bias sets, and even the analysis is like sort of by Fourier analysis of operators, very similar to the analysis of the de-randomized BLR tests. So that's that. And then to de-randomize this Hamiltonian, you can basically, it turns out if you have a PRG that's secure against quantum side information, that implies you can use it to de-randomize a Hamiltonian with many terms by just subsampling terms according to the PRG. And sort of like this, actually, by the security of the PRG, this actually has to preserve the ground energy of the Hamiltonian, because otherwise, like a quantum state that has like lower than expected energy would be sort of side information that would let you break the security of the PRG. So this is why, like, even though you're assuming that there's a PRG, you get like an information theoretically secure protocol out of this. Okay, and this trick is due to these authors. Cool. Okay. So this is this part. Now I'll get into sort of the main chunk of the work, which is analyzing the KLVY transformation of this protocol. So I have to explain how this transformation works, and I'll give you like a little peek into just like one part of the analysis. So I've drawn here, kind of tiny in this tiny diagram on the left. This is like a schematic of what an MIP star protocol is like, and I've introduced some letters here to keep track of what's going on. So the verifier sends challenges to Alice and Bob, which I've labeled by the letters X and Y. And they respond with outcomes which are A and B. And then the verifier decides to accept or reject. We can say it's computing some function, V of X, Y, A, and B. Okay. So now, what do KLVYs say to do to convert this into a single prover argument? They're going to kind of ask for a single prover to simulate both Alice and Bob from the two-prover protocol, but they're going to stretch out the simulation over time. So now we'll have multiple rounds of interaction. So there'll first be a round where the prover is acting as simulated Alice. Then there'll be another round where the prover is acting as simulated Bob. Okay, and how is the protocol going to work? It's going to use quantum homomorphic encryption. So it's going to say the prover should first prepare an encryption of the shared state that Alice and Bob would have shared. And now the verifier, instead of sending the challenge X, it will send an encryption of the challenge X under homomorphic encryption. And the prover will simulate whatever operation Alice would have performed to obtain an encrypted measurement outcome alpha. So this is why we're using homomorphic encryption, because it lets us compute on encrypted data. So you get back this alpha, which is meant to be an encryption of Alice's response. And then the verifier will send Bob's challenge, in this case with no encryption, and get back a response B that's meant to be Bob's response. And finally, what is the verifier going to do? It's going to now return, so it's the same function V, but it's going to apply it to X, the thing that was encrypted to send to Alice, the decryption of the response alpha that you got from the prover, and Y and B. Right, so you're basically just decrypting where necessary and checking did this pass the check from the two-prover protocol. So the intuition behind this is that although obviously the prover, there's no there's now full communication between simulated Alice and simulated Bob. Like simulated Bob can see everything that Alice sees. Alice's view of the world is sort of hidden under the encryption. So when the prover is simulating Bob, it has no idea what the question X was because it's encrypted. It only knows, just like how many bits long it was, and so on. It doesn't know what the answer alpha decrypts to either. So it's in effect, it behaves as if it's not allowed to communicate with Alice. Yeah.
So why is it so hard to prove the quantum soundness of? It almost feels like you're given the quantum soundness.
Very good. Yeah. Okay. So the reason it's hard to prove is that what you really want to say is that the reduced state visible to Bob for all different Alice challenges that you send should be identical. Then if it's actually identical, then there's a way to pull it apart into a bipartite state by purifying using Ullmann's theorem, right? And then you get a two-prover strategy. What you actually get is that it's not identical, but it's indistinguishable up to efficient operations. And so I don't know of any sort of computational Ullmann's theorem that will let you now pull this apart to a bipartite state. So that's what I see as the difference.
I see. So the computational statement would be that the states are different, purifications are different, but somehow the difference can't be detected by polynomial time.
Exactly.
I see.
Yeah. It's a great question. Okay, so this is the transformation. And now, okay, so what is the challenge in kind of analyzing this? So I guess like what we did is we showed like a bunch of, sort of standard MIP star tricks kind of port over to this world of the, the compiled MIP star. I'm going to just describe like one MIP star trick because sort of here the challenge was almost like actually proving the theorem was not very hard, but like sort of getting the right formulation was maybe a little bit harder. So there's a very common trick in MIP star analyses, which is called prover switching. And the idea is this. So suppose I have some sub-test in an MIP star protocol where I give Alice and Bob some questions, and I check that their answers agree. Right? This is a classic thing that you do in multi-prover interactive proofs. Like you want to check that both the provers are answering consistently according to some global object. So here, what can I prove is that if Alice and Bob agree in their outcomes with probability close to 1, then the measurement operators they use to obtain their outcomes must act in the same way on their shared state. So the state, Alice's operator tensor identity acting on psi is close in just the 2 norm, like the distance on states, to identity tensor Bob acting on psi. And this is super useful because it lets you kind of take a 2-prover statement about Alice and Bob and pull it over into like a 1-prover statement about products of operators on Bob's state. So now you can start testing for algebraic properties of these operators. We'll see an example on the next slide. This is a very common step that you want to execute in analyses of these things. Now, why is this kind of tricky to formulate in the compiled world? Well, in the compiled world, Alice is now, simulated Alice is acting under the encryption. So there isn't like a clean statement for the operator she performs in response to question X, right? Because what does the encryption do? Like if I'm asking it to encrypt X, it will actually sample some randomness and generate a random encryption of X, which is this ciphertext C. And then Alice will do something depending on the specific ciphertext C that she gets. And like it's sort of, it's hard to reason about like the average over all ciphertexts that encrypt, that are encryptions of the same X. Because even checking whether 2 ciphertexts are encryptions of the same X is not an efficient operation. It just makes it harder to make statements about the Alice operator in this world. It's much easier to model Bob's operator or simulated Bob's operator because in this protocol, the Bob challenge is sent in the clear. So so what we actually sort of formulate is like the version of prover switching that works in this setting is the following. So instead of talking about Alice's operator and Bob's operator acting in the same way on the joint state, what we actually show is that Bob's operator, if he agrees with Alice, then Bob's operator is close to commuting with the reduced density matrix that's visible to him, averaging over all answers that Alice gave, and over all encryptions of the same question X. So the lemma here is that if I take the decryption of Alice's answer and she agrees with Bob with high probability, then Bob's measurement operator commutes with the state rho enc of X, where rho enc of X is defined to be I take the average over all encryptions of X and I sum over all possible outcomes that Alice can give me. And this is actually a trace distance statement. So I'm saying like even though I'm making some assumption about cryptographic hardness, what I get out here is an information theoretic statement about commutation between this operator and this state. So why is this useful? Like why is this a substitute for the thing on the left? Well, let me just give you one little illustration of how the thing on the left is used in an analysis. So a typical thing one does with this prover switching operation is it lets you study things like the commutativity of different operators on Bob's space. So suppose I have one Bob operator, B1, that I know agrees with A1 by doing some agreement test on them. And I'm interested in some product of 2 operators, B2 times B1, on Bob's system. Now, using this, I can actually commute the B1 past the B2. How do I do that? Well, I have B2, B1 acting on psi. I convert B1 times psi into A1 times psi, right, by applying this equation. So now I have the A1 sitting in the first tensor factor over here. And now the next thing I can do is, so let's assume these operators are self-adjoint, so daggers don't mean anything here. I can act with the A1 to the left on the bra psi over here. So A1 acting to the left on bra psi is close to B1 acting to the left on bra psi. So I now get a B1 that appears on the left over here. So I've used this to show that kind of B2, B1 commute inside of an expectation value. Yeah, so this is like a typical manipulation you'd want to do. And now I'm going to show you that you can kind of reproduce that manipulation with this commutation condition over here. So what is this like object here? This is sort of the expectation value, if I marginalize over Alice, of what happens when I take B2 times B1 and I apply it to Bob's system. So what's like the analog of that? Well, it's just the trace of B2 times B1 on the post-measurement state of Alice, kind of averaging over questions that Alice gets. And here you can see that kind of to swap B1 and B2, it doesn't, directly from the cyclicity of the trace, there's no way to do this. There's no way to turn B2, B1 row into B1, B2 row. But if you can pull B1 through row to the other side, then you can use cyclicity of the trace to bring it back over here. So yeah, so this is just a little illustration of why this sort of simulates the behavior of that step. So that's all I want to say about the technical analysis of this. There's a bit more on the paper, so especially if you guys are interested in like group stability, we have some theorems here of how like group stability type analyses of monarchy star protocols can be ported over to this single prover world. I also think we have like a self-contained write-up of the De La Salle proof, since that De La Salle himself is a mathematician, and that proof is written in notations a little different from the conventions in quantum information. So if you're interested in that, I also would recommend checking out what we wrote. So to conclude, I just want to say like a couple words about what this might mean. So I guess today was like the quantum PCP day for this workshop. So one should always sometimes you want to take a step back and think about like where does quantum PCP come from? Why are we thinking about this? So you can go and check Scott's blog, and you'll see actually one of the first posts that he has on the quantum PCP theorem. He has this post, and he says, the quantum PCP manifesto, behold the PCP theorem, one of the crowning achievements of complexity theory. He goes on and he gives a conjectured statement, and he says, I'm 85% sure that the proof is achievable in a year or so, should enough people make it a priority. And he said, I bequeath the actual proving part to you, my readers. So then you scroll down, look at when did he say this? And it's from October 2006. So this was not solved in a year. And he has some interesting remarks that I think people have are still relevant today. One of them is that by analogy with the classical case, we'd expect that a full-blown quantum PCP theorem would be preceded by weaker results, like quantum assignment testers, et cetera, et cetera. We're still quite far from even like formulating the correct weaker results, I think, to prove. And then he also says, like, even for the quantum PCP itself, like maybe there's some questions about how to actually formulate it. And I think this we understand a bit better now, that for the full quantum PCP, like a bunch of different formulations are actually equivalent, but maybe for weaker formulations, we're not quite sure what the right weaker formulation is. So okay, so kind of motivated by this, you might think maybe we should actually go back to thinking about like weaker versions of quantum PCP. And maybe one strategy for coming up with a good formulation is to look for an application of a quantum PCP and then try to like, I don't know, weaken the application and maybe reverse engineer a weakened quantum PCP from that. Okay, and one application might be like succinct arguments for QMA. So why would you think about that in particular? Well, I mentioned at the very beginning that succinct arguments for NP are achieved using PCPs for NP, right? This is the Killian result. And there's kind of an inverse to this. There's a paper by Badan and Rothblum from 2010 that says that PCPs are inherent in some class of succinct arguments for NP. So provided that the security proof of the succinct argument is sufficiently nice, you can convert it into a PCP. And actually, the construction is very neat. It's like you write down your PCP proof is sort of like a big table describing the behavior of the prover in your interactive argument. And your PCP verifier simulates the verifier of the interactive argument, and it also simulates the hardness reduction. So the idea is that if a prover was trying to cheat, then there would be a reduction that takes the cheating prover and breaks some cryptographic primitive. So you just try running that reduction, and you see whether you broke the primitive. And if you didn't, then you believe that the prover is not trying to cheat you. So anyway, that seems kind of promising. But if you think about it, like that doesn't apply to the types of succinct arguments we have either here or in the BKLMMVVY paper. Because generating this PCP proof requires rewinding the prover to generate a PCP proof string, which is like it's supposed to be a transcript of all the possible things you might say. And like it just doesn't fit with the kind of security reduction that you have here. So yeah.
So what I brought the result is saying that assuming crypto assumptions, any succinct argument gives a PCP.
Yes.
Right.
Assuming a certain structure to like the security proof of your argument.
I see.
If it doesn't make crypto assumptions, right? It actually that's one thing that's cool is like you
Oh, good. Yeah.
need to make any crypto assumptions.
I see.
It's like, yeah, as long as your argument, like, as long as any like cheating prover to your argument could be used to break your cryptographic assumption, then you get a PCP that's like unconditionally secure. I think the statement. But I don't know how to make a result like this come through for these succinct arguments. And in contrast, we do have a very interesting result from 2023. So this is by Gun, Zhu, Ma, and Zandri. So it is known that succinct quantum arguments for QMA can be constructed using a quantum PCP in a kind of different world. So in the world of microcrypt, where you have cryptographic assumptions that are much weaker than even one-way functions. So there seems to be some interesting, I don't know, something going on here, in that like in the world of sort of mainstream cryptographic assumptions, this question of succinct arguments for QMA seems decoupled from quantum PCP. In this world here, you know, there's a construction from a quantum PCP to an argument, but I'm not quite sure how to reverse engineer it to get a. It's only conditional, right? There's no unconditional succinct argument for QMA in this world, but there's at least a relation to quantum PCP. So maybe somewhere in between, like if you, I don't know, twiddle the knob of cryptographic assumptionness, like you'll get some results that are relevant to quantum PCP. So that's my concluding speculation. And with that, thanks for listening, and that's the talk.
Yeah, thanks, Anand, for a great talk. Questions?
Just to make sure I'm understanding, like your use of the PRG is kind of weird, right? Like everyone knows the PRG seed, including like a malicious prover. Like you're using PRG security and the security proof.
Yeah.
Okay.
Yeah. That's right. Yeah.
I guess, could you avoid using the PRG using the stuff that Tina talked about earlier?
Oh, yeah, good question. Yeah, can we? Okay.
I think so, but whatever proved it better.
Actually, is it true that like, I don't know, like quantum games PCP was like a motivation for that construction, like the form of Hamiltonian term that you get there?
Sure, really why we did that.
Okay.
So, I guess maybe for Tzva was at that time I didn't know about PCP.
I see. Okay.
I guess so. To get the succinct answers, you're like doing kind of a composition with a classical PCP.
Yeah.
What prevents you from doing that inside of the MIP star system?
Oh, very good. It's sort of this issue of you need to check a predicate on both provers' answers at once, and so this can be done. Like this is done in like the MIP star equals RE kind of proofs, but that requires like one prover to be able to predict the other prover's answer if it knew the other prover's question. because then you can like do this oracularization transformation where you give it the other prover's question and ask it to prove something about both answers. This is not true for the teleportation protocol, because like essentially Bob doesn't know anything about like the state that Alice has, I guess. So yeah.
All right. No more questions. Let's thank Anand for a great talk, and also all the speakers, for their guys. So maybe another reunion next time. We'll do Umesh. Yeah. Thanks all for coming. Games.